I don't think so. I've just realized I've actually never used Google Meet to present anything, so
Okay,
I'm hoping it'll all work, but I know you'll be here in case something doesn't work and will be able to help me.
no problem. I was gonna say, normally for me, it works better if you want to see, like, if you want to see the meeting while you're presenting, you kind of have to have two like computer screens, like two monitors. If you have that available, it should work fine. If you don't, and it seems like it's causing you more trouble, you could always send me your files, and I could always put them up on mine if you need me to.
No, that should be fine. I'll
Okay,
figure it out.
sounds good. Sounds good. Alrighty. Okay, I'm gonna go ahead and get us started here. Um, Again, thank you very much to everybody that is attending tonight. Let me just go ahead and start the recording. Which hopefully, let's see. All right, so that pop-up should have came up. All righty. Well, welcome everybody to our April general meeting presentation. I would like to introduce you all to Dr. Matteo Luisi from Westminster College, which is the college I graduated from in 2009 before I went on to medical technology. So I was very super excited that Dr. Lisa responded. I kind of took a whim there and to see if maybe he would be interested. So I will turn this over to him. I would just like to remind everybody to please mute your microphones while we are doing the presentation. You will get a chance at the end of his presentation to ask your questions. If you need something immediately, just go ahead and type something in the chat room. For those that are joining us tonight on YouTube, I welcome you to the Amateur Astronomers Association presentation tonight. We will be following with our April general meeting at 8:30 p.m., which you are more than welcome to stay on for. And if you are new, I hope you enjoy. I hope you also like and subscribe. And I will turn it over to Dr. Luisa. Thank you very much.
Thank you. All right, let's see if we can get this to work. There we go. Can you see my screen?
Yes.
Wonderful. Can you see my mouse pointer too?
Yes.
Great. Thank you so much. And I will echo what Kristen said. If you have any immediate questions, please just interrupt me and ask. This will make things a lot easier. So to get started, today I'm going to talk a little bit about how massive stars influence their environments, but I wanted to start out with just giving you a little overview of who I am and what I do. So right now I work at Westminster College. I'm an assistant professor there of physics. We unfortunately do not have an astronomy program, but I get to teach one astrophysics class and another astronomy class together with coupled with an arts class that I'm really excited about. And I also run the planetarium at Westminster. I live in Pittsburgh, though, because I really like living in the city. So my background is that I originally grew up in Austria. I got my bachelor's degree in technical physics there, and I actually didn't know that I wanted to be an astronomer until I was sort of halfway through my master's degree, which was also in technical physics. After I finished my master's degree in physics, I applied for PhD programs here in the US, and I got accepted at West Virginia University in 2014. And that's when I started my PhD, and I just fell in love with interstellar medium astronomy, which I'm going to talk all about in a couple minutes. My wife and I have a dog. His name is George. He likes to be outside and go kayaking with us. And we also have a new addition to our family. This is baby Elliot. And please let me know if you hear any baby cries in the background. We just put him to bed, and he's in a phase right now where he absolutely hates to sleep. So if you hear a crying baby in the background, he's okay, I promise. He just doesn't want to go to sleep. All right, let's get started. So I'm going to talk a lot about massive stars today because all my research is about is essentially how massive stars influence their surroundings. So to make sure we're all on the same page, I'm going to start out with a little bit of background on massive stars and on star formation. And afterwards, I will segue over into the research that I do, namely how massive stars affect their surroundings on large scales, scales that are getting close to the size of our galaxy, and how they affect it on small scales. But small scales are still pretty large. We're still talking about several light years, several parsecs in size. Okay. How are massive stars formed? And I like this image here because it sort of shows an artist's expression of the stellar life cycle. You see here very little in the left bottom. This is sort of where a star lives most of its life. A star like our sun happily lived its life as a yellow mid-sized star down here for about 10 billion years. And then as it gets close to the end of its life, it'll blow up, follow this curve, turn into a red giant, and eventually explode and turn into a planetary nebula with a tiny white dwarf as its center. But right now we're talking about everything that happens up to the point where you see this little yellow dot in the leftmost corner. And the way I want to start talking about this is to talk a little bit about our galaxy at first. Because ultimately, when I talk about galactic evolution, what makes the evolution of our galaxy is really our stellar life cycles on large scale. Stars are being born, they live their life, and they die. And that repeats and goes on for the whole lifespan of our galaxy. Now, we live in the Milky Way galaxy, and because we live in the Milky Way galaxy, it's really tricky because we don't really know what our galaxy looks like from the outside. But we think our galaxy looks something like this. This is another galaxy called UGC 12158, and we think this is actually really similar to what our galaxy, the Milky Way, looks like. It's a spiral galaxy with the galactic center over here. Out of that galactic center emerges a galactic bar that exhibits rotation just like a solid object would. And then outside of that galactic bar, we see spiral arms forming. And those spiral arms also rotate about the center of that galaxy, but not like a solid object, rather as a wave where stars move into those spiral arms and then move out of those spiral arms, and so on and so forth. Now, if this were our galaxy, the Earth would be roughly here, roughly halfway between the galactic center and sort of the outskirts of that galaxy. So if we look at our own galaxy, the Milky Way, you all know when we look at the Milky Way in the sky, we see this band of stars and slightly brighter background than the rest. And that's essentially the band that we see when we look over here in this direction in the plane of our galaxy. And it's brightest when we look towards the galactic center. But what we don't see when we look at our galaxy, or if we look at other galaxies with optical telescopes, is the fact that there's a lot of stuff in the space between stars. We think about 90% of the total mass of our galaxy is in form of stars. So stars definitely make up a lot of stuff in our galaxy, but the space between stars is not empty. There's gas and dust in there. And that's what we call the interstellar medium, or ISM. That gas in the interstellar medium, that is mostly hydrogen, because most of the material in our galaxy is hydrogen. Hydrogen was by far the most abundant element that was formed in the Big Bang, and it still is one of the most, by far the most abundant element in our universe. And because the conditions in the ISM are very different depending on where you are, this hydrogen gas can exist in molecular form, where two hydrogen atoms form molecular hydrogen, can be neutral, or it can be hot and ionized. And even though the density of the interstellar medium is very low, if we took a piece of the interstellar medium and put it in a container on Earth, we would say it's a very, very good lab vacuum. But space is big, so if you add up all that material, it really is significant when it comes to the total mass of the material in our galaxy. When we talk about the life cycle of stars, we begin in what we call a molecular cloud or a nebula, which is basically just a giant cloud of dusty gas. So lots of molecular hydrogen in that gas because that cloud is cold and relatively dense. So when we have a cold gas cloud, that hydrogen will be molecular because there's just not enough energy to keep it in atomic or an ionized form. This is a picture I like to show my students, and they really, really struggle with this, but I'm sure you guys are much, much better at this than my students are. This is Orion. See Betelgeuse up here, nice and orange. Orion is also famous because it contains the Orion Nebula. It's one of the most famous molecular clouds in our galaxy. And if you look very closely, one of these bright patches is not like the other. There's one down here that is a little bit more extended and less point-like than the others. And while all the others are stars, this little one is. They look a little bit different than Orion because these are very dense and pretty cold. So even though there are some stars inside them already, we can't really see them because all that dust and cold gas is opaque to optical wavelengths. So we don't really see what's going on inside them. The only thing that we can see is light that gets reflected off their surfaces. So this is what happens. When we start out with a molecular cloud, molecular clouds are not very dense, but they're very large. So they still contain a lot of mass. And over millions and millions of years, gravity will slowly push that mass closer and closer together. You might start out with several molecular clouds. As gravity has time to affect that cloud, several molecular clouds might merge. As they become smaller, initially they heat up because all that gravitational potential energy is first converted into motion and then converted into heat. But then they also cool down because once we have a warm cloud, that cloud will emit light and that will remove energy from the cloud. And eventually we'll end up with a pretty dense object that's called a protostar. That protostar is the precursor of a star. It is already bright because it is hot and dense, and it still gains mass from the molecular cloud, which maintains its energy, which puts more energy into the protostar. Because the molecular cloud initially probably had some rotation, the protostar itself rotates, and it will form a disk around itself called the protoplanetary disk that also rotates. This is an actual image of a protoplanetary disk. Right here in the center, you have the protostar. This is the disk. And you can take a guess at what is happening in there. You see how there are parts of that protoplanetary disk where it looks like we don't have any stuff. Those are orbits in which the precursors to planets have already formed. So that's stuff in the disk that tends to clump together, and eventually those clumps will become bigger and bigger, and they will sweep up everything in their orbit. So this is essentially similar to what our solar system looked like 4.5 billion years ago. This image was taken with the ALMA radio telescope, where you essentially have a bunch of radio telescopes that form one large virtual dish, and that gives us the resolution to actually explore these very small protoplanetary disks in detail. The protostar keeps contracting because gravity is still going on, and eventually the center of the protostar becomes dense and hot enough that hydrogen atoms can fuse into helium. So you'll have 4 hydrogen atoms that will form a helium atom, and in that process it gives off energy. That's called nuclear fusion, and it's what powers stars. And for a star like our sun, that process will go on for about 10 billion years or so until most of the hydrogen in the core of the star has been used up. Okay, so now I want to switch gears just a little bit and talk about more massive stars than our sun. So far, everything I've said was applicable to really any star, but specifically I want to talk about the most massive stars that we have in our galaxy for reasons that will become clear in a little bit. And those stars are O-type stars. They have at least 15 times the mass of the sun. They're much, much hotter than the sun, about 8 times as hot. Sun is about 6,000 degrees Kelvin. O-type stars are about 40,000 Kelvin or so. And they're maybe 10 times bigger in radius than our sun. So just from the bigger size, you might expect, okay, if the radius is 10 times as big, they might be 100 times as bright because their surface area is 100 times as large as the sun. But in fact, they're about 100,000 times as bright as the sun, as luminous as the sun. And that's really due to their high temperature. They shine very, very bright. And that's good because a very small fraction of stars are O-type, but because they shine so bright, a lot of the radiation that exists in our galaxy is due to O stars. So even though there's not a lot of them around, they really have a large effect on what's going on around them. Because they're so bright, because they're so hot, they don't just emit a lot of visible light, they also emit a lot of high energy radiation. So here we're talking gamma rays. And when I say high energy radiation specifically, I mean radiation that is energetic enough to ionize hydrogen. So what happens is you have some atom, for example, hydrogen, happily floating around that star, minding its own business. Suddenly a photon radiation from that star will hit the electron and essentially knock it off. And what you're left with is a free electron and a positively charged rest of the atom. And what happens as a result is that when we look at a region around an O star, that region is fully ionized. And because that region is mostly made up of hydrogen, we call it an H2 region. And I want to apologize for astronomers all around the world because astronomical notation is strange. H2 with the Roman numeral 2 talks about ionized hydrogen. So that's essentially just free protons and free electrons. H with the Roman numeral 1 is neutral hydrogen. And H with the subscript 2 is molecular hydrogen. So when I say H2, it really could be either ionized hydrogen or molecular hydrogen, and there's no way for you to know which one I'm talking about. But I will tell you now, whenever I say H2 for the rest of this talk, I'll be talking about ionized hydrogen. So we have this region around the O-type star that's fully ionized. We have this H2 region. But the surroundings of O-type stars are not nice and homogeneous. So depending on which H2 region we look at, things can look very different. Sometimes all that radiation around the star can push away the surrounding molecular cloud, and it might look something like this picture where you have a very bright star here, and then sort of some fragmented small molecular clumps around it. Or it might look like the pillars of creation, where that molecular cloud is still very intact, and any stars that have formed inside that molecular cloud are just obscured because there's so much material still around them. Excuse me. When it comes to H2 regions, again, depending on the morphology of the stuff around them and depending on the type of the star formed in the region and depending on whether we have one O-type star or several, they can have very different sizes. Sizes range from much smaller than a parsec to much larger than 100 parsecs. Just so you know, if you want to convert between parsecs and light years, 1 parsec is a little bit over 3 light years. So just for comparison, our solar system is about 1,000th of a parsec. And the nearest star to us, other than our sun, Proxima Centauri, is about 1.3 parsecs away. And our galaxy is about 30,000 parsecs or so in diameter. So these H2 regions are very large compared to the size of our solar system, but they're still pretty small compared to the size of our galaxy. They sort of encompass several stars usually. And again, several of these stars can be high mass stars, and that just depends on how they were formed. Now, when we look at these H2 regions, they look very different depending on which wavelength we look at. Over here on the left, you see an optical image. So in an optical image, H2 regions often look a little reddish. And that's because ionized hydrogen gives off a red emission line. And so you often see this reddish hue. You often also see a bluish color, and that's not from the H2 region itself, but it's rather light from the O-type star that is reflected off gas surrounding the H2 region. Now, things become pretty interesting once we look at infrared wavelengths. In some infrared wavelengths, we see a ring-shaped emission around the H2 region, kind of like this green emission we see here in the middle panel. And this ring-shaped emission comes from something called polycyclic aromatic hydrocarbons. This is a image that I actually did for a paper several years back, where we studied several H2 regions and looked at their sort of ring-shaped emission to see what we can find inside the H2 ring and outside of that ring. So what happens here is that in this ring, we have lots of polycyclic aromatic hydrocarbons, or PAHs. PAHs are carbon rings, essentially, large carbon ring molecules. And if the radiation that hits them is energetic enough, then it can excite these molecules and they start vibrating and rotating. And then as they vibrate and rotate, they give off infrared emission, and that's the infrared emission that we can see. Now, the radiation that hits them to produce this infrared emission has to be very specific, because if the radiation is too energetic, it will break up the bonds between the carbon atoms and destroy the PAHs, and then we have no emission. But if it's not energetic enough, it won't excite the PAHs, and they won't start rotating and vibrating. So usually we find these rings just outside of the fully ionized H2 region. And this is sort of the picture I have in my head of what's going on. You have an O-type star in the middle. That O-type star gives off lots of energetic radiation. It ionizes everything around it, and that makes up the H2 region. Now, on the outskirts of the H2 region, all that ionizing radiation has been used up. It has ionized everything around it. There's no more ionizing radiation left, but there's radiation left that is less energetic. So this radiation now travels a little bit further out and excites the PAHs. In that region where we have this ring-shaped emission, where we have those PAHs, that's what we call the photodissociation region, or PDR. That's a region that is mostly neutral. The gas in there is mostly neutral, not much is ionized, but the gas chemistry is still very strongly affected by this high energy radiation. And then as we go further out, we have atomic hydrogen, then we have molecular colder hydrogen, and that whole region is sort of embedded in the larger interstellar medium in our galaxy. So this is this nice picture, kind of like an onion, where you have these individual shells. Here's the problem, though. We don't really observe that. What we observe is more like this. We do have this shell structure, but at the same time, some energetic radiation, some ionizing radiation from that O-type star can just escape and travel far away into the interstellar medium. So what we think is happening is that there are some low density pathways in those shells where this radiation can just travel through. And that makes it a little bit more difficult, as you can imagine, to study these regions, because now we have to think about, okay, what is this radiation doing out here, right? So this was a study that was done by Lauren Anderson about 10 years ago, where they tried to maybe not fully quantify how much radiation leaks, but just show that radiation leaks and that it leaks across very specific pathways. This is an H2 region called RCW120. It's often considered the poster child of H2 regions because it's really, really nice and round. It has very nice circular symmetry. And what you see here in green is a contour for dust temperatures. So essentially, this green contour tells you that everything inside that green contour is hotter than, I believe it was 45 Kelvin or so, and everything outside is colder than that. So you can see where this contour kind of pops out a little bit, like down here and here and here. these are regions where the H2 region is hotter near its boundaries. And that's an indicator that towards these regions, and they're also indicated with these green lines out here, towards these regions, some radiation can escape through this H2 region boundary, and then it will heat up stuff that's outside. Where I looked at a different H2 region, NGC 7538. If you look over here to the right-hand side, you see these white lines labeled with PDR. That's sort of the PDR boundary around this region where we say, okay, we think everything inside this boundary is ionized, everything outside is not ionized. That's radiocontinuum emission. And radiocontinuum emission comes from ionized gas. And you can see by just comparing that boundary in the right picture and all the emission we see in the left picture, that there is a lot of emission outside of that PDR boundary. Lots of ionized gas out there. About 15% or so of the total ionized gas we find outside of that boundary. So that was sort of our first proof that some of that ionizing radiation has to leak out and ionize stuff around the H2 region. This region in particular lies in the outer galaxy. There's not a lot of stuff around it. So we're very sure that this ionized gas is really ionized from the star in here and not from some other source. Okay, so now we are really going to dive into my research. And I would like to start with what I've done on this escaping radiation from high mass stars and how that affects the interstellar medium on very large scales. So when I say large scales, I mean scales that are maybe not the size of our galaxy, but they are significant compared to the size of our galaxy. Okay. So this image we have here, that is an image of H alpha emission. So that's another way to trace ionized gas. And if you look at this emission, you see that there's a lot of ionized gas essentially everywhere in our galaxy. This image encompasses more than half of our galaxy. A lot of these bright blobs are individual H2 regions. So we would expect ionized gas to be there. But there's also a lot of ionized gas that is not associated with any particular H2 region. And that is what we call the warm ionized medium. It is part of the interstellar medium that is ionized, and we believe it is ionized from radiation that is escaping from individual H2 regions. The image on the left shows the warm ionized medium in a different galaxy, NGC 157. All the black circles are individual H2 regions, so they were just removed from the image because right now we don't care about the H2 regions themselves, but what we do care about is all this ionized gas that is sort of mixed in with the diffuse interstellar medium. So I want to observe this warm ionized gas. I want to know where we can find it exactly in our galaxy and what its properties are, and how we can relate those properties to H2 regions. But it's tricky. If we do things in H alpha like they did, it gives us a really nice large map, but we have a lot of dust in our galaxy. And dust, as you probably know, if you've ever pointed the telescope towards the center of our galaxy, dust obscures a lot of the stuff that lies behind it. And so if we observe this in optical emission, we cannot get a full synthesis of the total warm ionized medium. There's just too much dust that blocks the light from it. This is another image of H alpha emission in our galaxy. You see very nicely individual H2 regions. You also see those bigger blobs. Some of those are from supernova remnants. But over here, for example, you see how it's pretty dark here. And that's not a lack of H2 regions, it's just foreground dust. So it makes it really hard to figure out where exactly we have this ionized gas. And here's my solution to that problem. I am a radio astronomer. I do a lot of things with radio telescopes, and I love it because with radio emission, we don't have to worry about dust. Radio light, radio wavelengths can travel straight through the dust and come to us and not be attenuated at all, essentially. And for the most part, for my research, I use the Green Bank telescope. I don't know if any of you have ever had the chance to go down to Green Bank. Green Bank is in southeastern West Virginia. It's in Pocahontas County, about, I want to say maybe 4 hours from Pittsburgh or so. And it's the largest fully steerable radio telescope in the world. You can kind of get an idea of the size of it by comparing the size of the telescope with the people that are standing in front of it. The dish has an area that's comparable to the area of the football field. Really, really cool. If you ever drive down there, make sure to stop. They have an amazing visitor center, and sometimes they offer tours that will actually take you up onto the telescope. When I was in Greenbank for the very first time, it was foggy, and we went on a tour up the telescope. And I remember standing right over here at the edge of the dish, and I would see almost the entire dish in front of me, but I would not see the ground because it was so foggy, and it was the most surreal experience. There was also a time we were able to go up all the way up here. This is the receiver cabin. So what happens is radio light comes in, gets reflected off the dish into the receivers. So this is a little cabin that's about, I want to say maybe 150 meters above ground. So it's kind of crazy how large it is. So what I observed with the Greenbank telescope are so-called radio recombination lines. So what happens is when you have ionized gas, that gas does not just stay ionized forever. Eventually, those free electrons and ions will find each other, and they will recombine to form a neutral atom. That neutral atom might get ionized right away again, but it will form a neutral atom first. And whenever it forms that neutral atom, whenever it recombines, that electron does usually not go straight into the ground state, the lowest energy state, but it goes into a high energy state and then it cascades down into the ground state. And every time it jumps one energy level, it emits light. And a lot of these jumps are in the radio regime, so we can see them with telescopes like the Greenbank telescope. And what's really nice is we don't just get an idea of how much ionized gas there is, we also get the velocity of the ionized gas along the line of sight. And we do that with the Doppler effect. We know exactly the frequency of the radio waves that the emission should have when it comes to us, but oftentimes that frequency is shifted a little bit. If that gas is moving away from us, we expect that frequency to be shifted to lower frequencies. If that gas is moving towards us, we expect it to be shifted to higher frequencies. This is just like listening to an ambulance. When it's coming towards you, you hear a higher pitch. When it's moving away, you hear a lower pitch. It's the same thing just for radio waves. And so that tells us this frequency shift, and then we can convert that frequency shift into a velocity. So what we get out is a so-called spectrum, where we see the total intensity, how large, how tall this line is. That tells us the amount of gas that emits. And where that line lies on the x-axis, that tells us the velocity of the gas. So right here, we observe a very strong hydrogen line at about minus 60 kilometers or so, which means that hydrogen line that we observe there is moving towards us with a velocity of 60 kilometers. And we studied a large complex of H2 regions called W43 with those radio recombination lines. This is what the image looks like. The one downside of radio astronomy is that our resolution is generally pretty poor, so everything looks a little blurry. But we can already see here there's a lot of ionized gas here, a lot of ionized gas here, and quite a bit sort of distributed all around. Okay, a lot of this gas comes from H2 regions. We're not interested in H2 regions. We want to know where the diffuse gas is, the warm ionized medium. All these circles you see here are individual H2 regions. We have mapped these H2 regions in a different study using infrared emission by looking at this ring that I've showed you earlier. So we know where all the H2 regions are, and we can remove them from the image we took. And all the emission that is left after removing all of those circles, that's emission that we think that is just due to this warm ionized medium. So that's just diffuse ionized gas. And we think that this diffuse ionized gas must have been ionized by radiation that was leaking through those H2 regions and into the broader interstellar medium. And you can see it's kind of cool because we do see a lot of this gas close to H2 regions, which would kind of expect, right? If radiation leaks out of an H2 region, it will ionize the stuff that's nearby, but some of it moves very far away. So we think this radiation can travel far through the interstellar medium. And we want to figure out why. We want to figure out how that radiation can travel so far away. And there are some theories. Usually, it shouldn't be able to do that because there's a lot of interstellar medium around, and it should hit something earlier. But one theory is that supernova explosions can create large cavities in the interstellar medium, essentially regions with very, very low density. And if radiation travels through these regions, it could just travel through unimpeded. And another possibility is that the interstellar medium itself is not this homogeneous gas, but rather that it is made up of lots of filaments, lots of little sheets, and that in between those filaments, there's very little stuff, and in between those filaments, that radiation could travel more easily. So to figure out which of these models is more likely, we created a computer model of what we expect the emission to be like. We said, okay, we have all these individual H2 regions. If we assume that each H2 region leaks some fraction of its radiation into the interstellar medium, and we assume some fall off, some probability that this radiation will interact with stuff around the H2 region, we get out a distribution of the ionized gas like this. If you compare this to the data, it looks somewhat similar. You can ignore that the data is more blobby. That's just an artifact because our resolution is pretty small and we have some noise. But something that we see in the data that we do not see in the model, for example, is this emission down here. This is almost like a filament that extends downwards. There's also a little bit over here on the right-hand side. And so the real data is definitely a little bit more filamentary. Oops. And this is something that we would expect from the interstellar medium itself being more filamentary. If we had big bubbles where we had supernova-driven cavities, we wouldn't expect these relatively narrow filaments. We would expect basically a larger, more homogeneous distribution compared to the model. So that's our theory, but right now it's still really hard for us to tell because this is only one region of the sky that we've looked at. And even though we spent a lot of time on taking these data, taking this map took about 50 or 60 hours with the Green Bank telescope. We still have a lot of noise in that map because that gas is so diffuse. So definitely some follow-ups we need to do. Okay. This is what we've done on large scales so far. Now I want to focus on the smaller scales. And when I say small scales, I'm talking about scales the size of an H2 region or so. Here we'll be talking a lot about stellar feedback. And the idea is essentially that whenever we have high mass stars, those high mass stars can influence their surroundings through a variety of mechanisms. They can have jets and outflows as they are being formed. Once they live, they have lots of high energy photons, high energy radiation. We already talked about that. Those photons also have momentum, so that radiation can push stuff away. We have stellar winds. Again, supersonic winds, mass ejections from the star that can push things away, create shock fronts. And at the end of their life, they explode in supernova explosions. And what's interesting is that the stellar feedback can be positive or negative. So what that means is that this star that we have in the H2 region will affect its surroundings. It will push that gas around it around. And sometimes it can push it around in a way that it pushes other gas clouds together. And when those gas clouds are pushed together, they're more likely to form new stars themselves because their density suddenly gets larger. So that's what we call positive feedback. But on the other hand, feedback can also be negative. All those feedback mechanisms can rip apart gas clouds and make it less likely for them to form stars in the future. So if we have an H2 region, what happens in the surroundings of the H2 region could be that a lot of stars are being formed because of positive feedback, or no stars are formed because of negative feedback. And it's really, really hard to tell from initial conditions which of these will happen for a particular region. Very small changes in the initial conditions can drive positive feedback to negative or vice versa. An example for positive feedback, you can actually see in Orion, lots of regions within Orion where we have fresh protoplanetary disks where gas has been pushed together to form new stars. Orion is a little tricky to analyze though, because it is a pretty complicated region, very asymmetric, lots of different gas densities we'll have to work with. So this is not what we looked at. We looked at this H2 region I showed you previously very briefly called RCW120. In RCW120, we have only one ionizing star in the center, one O-type star. And around its boundary, we have lots of protoplanetary disks and protostars. Those are all those red dots. So we think there's some positive feedback going on down here, and we want to explore that further. And we actually did that not with the Green Bank telescope, but with SOFIA. SOFIA, I think I said before that the Green Bank telescope was really cool. SOFIA is even way cooler than the Green Bank telescope, or rather it was. Unfortunately, it doesn't exist anymore. SOFIA is an infrared telescope mounted in the back of a Boeing 747. This was a mission, a combined mission between NASA and the German space agency, where they essentially took a 747, stripped out the entire interior, put that telescope in the back, and then all that equipment to operate that telescope in the center of the plane. And because the telescope is so heavy, they had to strip the plane from everything that was non-essential. So if you're on the plane, it's really, really loud because there's no noise insulation. And it's really cold because there's no heat insulation. I actually got to fly in SOFIA, which was awesome. On the left picture here, this is taken roughly from the center of the plane looking backwards. So what you see here in the background is sort of the back end of the telescope. So everyone's operating their telescopes, and I was just a guest, so I just stood there and took pictures, basically. But you can see it was pretty cold. Everyone was wearing their coats, and we all had noise-canceling headsets because it was pretty loud. So with SOFIA, we observed the C2, the singly ionized carbon line. And that line is another way to trace this photodissociation region. So this line essentially traces the same things that PAS trace, but with the C2 line, we can also get velocity information, which is really important. And this is what our data look like. So if I go back and forth, this is our infrared data, which looks really nice, but it doesn't tell us anything about the velocity of the gas. And this is our C2 data, which looks a little less nice because we don't have quite the sensitivity or the resolution. But for each of these pixels in the map, we get a full spectrum so we know how things move. And this is how things move. And this is a little complicated to understand, but I'm going to walk you through it. So this is a so-called position velocity diagram. On the x-axis, you have position. So going from the left to the right, that will be the same as taking this image and going from the left of this image to the right of this image. But when you go up and down, this is now the velocity information that we have. So gas that lies along this dotted line, that is gas that has a velocity of -7 kilometers per second. So that is gas that moves towards us with 7 kilometers per second. So that tells us that on the left side of the region, there's a lot of gas that moves towards us with 7 kilometers per second. And there's a lot of that gas on the right-hand side, but not quite as much in the middle. But if we go down here, that's where gas sits that moves towards us with 20 kilometers per second. And so that tells us that towards the center of the region, some of that gas moves towards us with 20 kilometers per second, much faster than the gas that sits on the sides of the region. And whenever we see these arcs in position velocity diagram, that essentially tells us that something is expanding. So this in particular tells us that half the front half of this region is essentially expanding towards us. And it's expanding fast with about 15 kilometers per second. We did an energy analysis. We found out that it's the stellar wind from the O-type star that drives this expansion. But what was really interesting is that because it's expanding so fast, this region must be very young. And when we say young in terms of H2 regions, is anything less than 1 million years, essentially. This region in particular, we think, is only about 150,000 years old. But we see that there's already been triggered star formation in the boundaries, positive feedback that caused new stars to be formed. And that tells us that positive feedback can operate on very, very short timescales. It doesn't take long between H2 region sort of starting to exist, starting to drive stuff outwards, and new stars being formed just outside of that H2 region. I'm not going to go into much more detail here, but one thing I wanted to mention is that this has implications on larger scales as well. And in particular, in the early universe, we know there was a phase where we had very high star formation rates, where a lot of stars were being born, many more stars than we think should have been born, given sort of the mean density in the universe. And we postulate that that might have been due to positive feedback. You have one high mass star that's being formed, and that triggers a whole flood of other stars to be born around it. And if that happens everywhere in the universe, we would sort of see global star formation rates go way up, and lots of stars would be born in a very short amount of time. So this is where I'm going to end. I'm going to leave my summary slide up here. If you have any questions, please ask. I know this was a lot of information, but I'd love to hear your thoughts and your questions on this. Thanks, everyone.
Thank you so much. That was very interesting. It's like bringing back to the physics days. Does anybody have any questions? Mary, Mike, Fair, I see your hands up. Mary, did you have a question?
No, I was just trying to send feedback. I think I hit the wrong button.
Oh, okay. All right. Mike, did you have a question? I think it was Mike Fair that I saw. Okay, maybe not. All right. I know Eric's hand is up. Eric, did you have a question? You need to turn your mic on, Eric.
You saw my lips moving, right? This is a little bit off topic, but in the beginning, you're talking about these massive stars having X number times the mass of the sun. And this goes back to measuring standards, because there's something called the Chandrasekhar limit of 1.4 solar masses, beyond which you can't exceed, otherwise something happens, a black hole or whatever. So can you just sort of clarify for us this business of maximum solar masses in a star, the measuring and the implications?
Yeah, absolutely. That's a good question. So the Chandrasekhar limit that you mentioned, that has to do with what happens with a star after it dies. So you can have stars that are 15 times the mass of the sun, but if they exceed that Chandrasekhar limit, which I think is, oh boy, I should think back to my astro course because I haven't taught that in a while. I want to say about 8 times the mass of the sun or so.
Yeah.
Then that star will die in a supernova explosion and form a black hole.
Right.
If it's less than that, it will still have a supernova explosion, but the remnant will be a neutron star. And if it's less than that, it will shed out its outer layers in the planetary nebula, and the remnant will be a white dwarf. For example, that's going to happen with the sun.
Mm-hmm.
So we know that pretty well. What we don't know very well is the largest mass a star can have during its lifetime. So as we go to more and more massive stars, there are much, much fewer of them in the galaxy. So I said, let's see, 0.00003% of stars are O-type. Most of these 0.00003% of O-type stars are actually pretty low mass O-type stars. Those are stars that have about 15 times the mass of the sun. Once we get to stars to about 25 times the mass of the sun, there's only maybe tens of those in the Milky Way. And the most massive star in the Milky Way has maybe 30 to 40 times the mass of the sun. I'm not sure on those numbers, but the main point is that essentially as you go up in mass, it becomes really rare. And so we don't really have a good observational limit of what the highest possible mass for a star is. From theory, we know that stars cannot be more massive than, I want to say, about 200 times the mass of the sun, because then they destabilize internally and essentially shed out their outer layers during their lifetime, and that reduces their mass again. But we don't really know what happens between those, like 40 times the mass of the sun and 200 times the mass of the sun, what's potentially possible and what isn't. But so basically everything 15 times the mass of the sun or more is enormous in terms of its luminosity already.
But just as a follow-up, in other words, for these massive stars, you know how in the sun we're fusing hydrogen to helium, then helium to blah blah through the periodic table, and you get to iron and things stop. Does the same thing apply with the more massive stars? You get up to iron, and then boom.
Yes, it does. So in our sun, things really stall a little bit before iron. Our sun will fuse hydrogen into helium, and I think it will fuse some helium into carbon, and then it sort of stalls in terms of its mass. And the next lower element, and then at some point you have carbon, and then you have helium, and then you have hydrogen. And yeah, and anything heavier than iron is really just formed in highly energetic events, mostly supernova explosions, where atoms just hit each other with really, really high energies, and then they'll fuse together, even though it's not energetically optimal for them.
Right. Thank you.
Yeah, of course. Good question.
Ken, you have a question, or Priscilla?
We know you're there.
I was gonna say, Ken, are you able to turn your mic on or off? It looks like it's on. We just can't hear you. You might have to turn your volume up. Do you want to put something in the chat? Okay, go ahead. I think we're just typing. Let's see here. Oh, can you use these environmental effects to measure the mass of large stars to see how big they can be? Is the question.
To some extent. The problem is really that when we have a very high mass star, like it affects its environment in lots of ways, and that can tell us exactly how massive that star is and how much radiation it gives off. But it doesn't really tell us what would happen if that star was bigger, if that makes sense. And there just aren't any really, really big stars in our galaxy that we could use to test that. Does that make sense? Did that kind of answer your question?
Yes, it does.
We hear you now.
Yeah, I finally found this setting. I'm not used to this program either. Thank you.
All right. If you don't mind, I'm going to ask a quick question. So whenever you were initially, I think it was after this slide, but you were talking about basically those gamma rays getting through, like going through the outside of those layers, and you were talking about the kind of the onion effect. You were talking about that massive star technically still being the center, and that ray effect going outward, correct?
Mm-hmm.
So then one of my other, I think, was it outside the is it the PDR or the H1 that those stars would be forming then?
That's a good question. So it's kind of hard to tell because this is sort of the optimal model. And in reality, things get kind of muddled. And in reality, that PDR, like that H1 layer, might be really, really small or essentially non-existent. Where these stars would form would basically be in the molecular hydrogen layer over here, in the H2 layer. But because when we have very strong feedback, everything gets kind of pushed together, it's with our resolution, we can't really tell exactly where those stars are. So yeah, somewhere around there would be the answer. It's also tricky because those stars themselves give off energy. So once those stars are formed, there isn't really an H2 layer right around them anymore. But initially, they must have been formed from molecular gas because that's the only phase that is dense enough to form stars. So this is really an idealized view that we like to think of, but in reality, things get muddled a bit more than we'd like.
I found it curious only because well, you know, like the fact that those gamma rays are, you know, traveling so fast and yet like you have that barrier there, so it's making its way kind of through that barrier in some ways. Like, you know, it's not like a huge how should I say this? Like, I don't want to say there's, you know, those big holes, but it's kind of, at least from how you were talking, you can see where, yeah, like that example.
Yeah, let me see.
But what I was kind
Um,
of curious about is, you know, since if the reactions are happening in those layers, if that, in, I don't know if I might be overdoing thinking it, but in theory, like if those reactions are taking place around those barriers or those layers, if that's why you see just those certain like emissions of those rays. That's kind of what I was wondering, if that was a possibility.
yeah, so there's really two different effects at play here. So on one hand, if you look at this green boundary over here, this is essentially the photodissociation region where the PAS live. And there are some parts of that that are a little broken. Like here, for example, on the left, you can see it's a little less dense, or like down here towards the south, and then we have this big hole towards the north. Like you'd imagine that some radiation can just travel out in those regions, and that radiation could go really, really far. But then at the same time, like whatever the star does in terms of its stellar wind or photon momentum, that will push the boundary itself and make it denser, and that's what causes those new stars to form around the boundary. So we think these two are kind of related in that when we have sort of these breaks in the PDR boundary, that we wouldn't expect any new stars to form there because there's just not enough material there. Um, but yeah, but then through those breaks, we would see that emission escape. Did that kind of make sense?
Yeah, I think my mind was going, those barriers are, because you figure you're looking at this from so long ago, and you know, obviously, but I'm thinking like those barriers are like, we're still seeing them, obviously, again, distance, but like if those barriers are still kind of there because those stars are forming, I guess that's like where,
I understand now.
yeah, like that's kind of what I was wondering, if, you know, so you see those, like you just said, you see those breaks, which I totally understand that part, because that's just the break in the barrier, but that being able to hold that barrier on, you know, the bottom part of the left right side, that's what I was wondering.
Now I understand. That's a good question. And I think the answer is not really. And the reason I say that is because star formation is relatively inefficient. So when you have a big molecular cloud and you form a star in that cloud, it's usually just a percent or so of the cloud material that actually goes into the new star. So even though we have a lot of new stars being formed down here, there's still a lot of that barrier material there. And we don't really expect those individual stars to affect that barrier material too much because those are not likely to be high mass O-type stars. And it's only really O-type stars that would affect that barrier material very much. So I don't want to say I can answer this conclusively, but my guess is these stars won't affect the existence of the barrier very much, even into the future. Good question, though.
Thanks for understanding my question. I was like,
It was
how do
it was a good question. I had never thought about it. It was good to think about it.
All right. Does anybody? Oh, Eric, do you have another question? If
I don't
you're
wanna-
okay.
I don't want to hog the questions from other people, but just a very quick question, sort of off topic again, really off topic. T Corona Borealis, the variable star in Corona Borealis, if it exploded while the constellation was behind the sun and then it comes into view again, would we know that the star has erupted? Maybe in the spectrum? This might be out of your field of knowledge.
I don't know what that star is. Is that a high mass star that's
Yeah, there's
close
a high
to the end
mass
of its
star and
life?
a white dwarf, and it's the white dwarf is pulling matter off the giant
Okay.
star, and then it pops
Okay, gotcha.
every 80 years. And if it did it while it was out of view behind the sun, would we know just by
Yes.
looking at the spectrum?
Yes, we would. So that would be a type 1 supernova, and those usually glow for a while. So the initial eruption, like, let me think about the timelines here. It usually takes about a few minutes to an hour or so to go from like regular star to the brightest point in the eruption.
Mhm.
But then it takes days to weeks until that dims. And the reason is it's not just like a big explosion where everything is hot for a second and then it's cold again, like we might have on Earth, but you have lots of hot material that's still around the star that still glows very, very bright. So yes, we would definitely see it, and all the astronomers in the world would point their telescopes toward it for the next few weeks to see what this afterglow would look like.
Thank you. I didn't want to stretch out the meeting too much, Kristen. Thank you.
No, you're fine. Does anybody else have any questions? Greg, do you have a question?
Yes, thank you so much for this. This was a very good talk. My understanding is that these massive stars don't live long. And I mean,
Correct.
like the sun, like 10, 15 billion years. We're talking like tens of millions or hundreds of millions of years. So the ones that we're observing now are very young. And there must be throughout the galaxy, there must be just sort of remnants of these black holes, I would guess, that I don't know, are sort of their remnants detectable through these means? That's sort of one question. And then sort of another question that isn't really related is, given the spiral nature of the galaxy that we're in and Andromeda and the other ones, there's also around us all these little dwarf galaxies. Do we see this phenomenon in those as well? Can that be observed, or is there just some dynamic in those galaxies that sort of prevents this or whatever?
Let me answer the second question first, because that one's easy to answer. The answer is yes. We totally observe that in the dwarf galaxies too. There's lots of studies on that in dwarf galaxies. I didn't talk about it here today because I had enough to talk about already, but yes, we definitely observe that in our dwarf galaxies. With dwarf galaxies, it's just a little bit tricky because they're far enough away that we don't get the resolution we would get from an image like this. But then they're also so small that we don't really get like the global properties it would have on a full regular galaxy. So the studies are a little bit limited in what you can get out. Now, as to your other questions, yes, O-type stars live tens of millions of years, which is very short. So we actually call them zero-age objects, because essentially when we see an O-type star, that tells us this is a region where star formation has just happened, because otherwise that O star would already be dead, right? The thing is with O stars, when an O star dies, like after the initial supernova, crazy explosion, etc., that H2 region doesn't really exist anymore. That H2 region is usually just swept up by the supernova explosion, and we can observe these supernova remnants, but not for very long. So after an O star dies and sort of takes its H2 region with it, say 10 million years later, it's kind of gone. We can't really observe things anymore. So we do think there's a lot of black holes out there. We think there's a lot of neutron stars out there, but we can only observe those under special circumstances. Black holes are very dark, as their name suggests, so it's hard for us to see them unless they're actively swallowing something. And neutron stars are very small, so they're also really hard to see unless they're a pulsar. So there's lots and lots of sort of these dead remnants floating around our galaxy, but we don't have a good way of observing them.
Alrighty. Well, Dr. Luisi, I'm sure we can go on and on like talking.
This is great. I love this.
All I can say is awesome presentation. Thank you so much for joining us tonight and you know,
Thank you guys
sharing.
for having me. I really appreciate it.
Yeah. If you are okay with it, obviously, I found your email, you know, because I emailed you to do the presentation. Are you okay if I share your email with the group? If anybody has any further questions or, you know, would like some more information, they could reach out to you if that's okay.
Absolutely.
Okay.
Yep, absolutely.
All right, great. Well, again, thank you. I'm going to go ahead and let everyone take like a 5-minute break, and then we're going to start our general meeting. You are more than welcome to stay on if you would like, or if you, I'm sure you were probably little run
I
out.
appreciate the invitation, but with a little baby at home, I'm gonna go to bed and get some sleep. But I do
don't blame
appreciate
you.
it.
I don't blame you. Well, thank you again, and I'll send out your email address, and you know, maybe at some point we'll keep in touch, and you can let us know if you went any further on your research as
Yeah,
well
I'd
too.
love to.
Or if
Thanks
you'd like to
everyone. This was fun.
talk in the future too.
All right, thank you. Have a good night.
Thanks everyone. Have a good one.
Thanks.
go ahead and get started. I'm going to go ahead and start recording again. Brian, if you are good to go. Okay. All righty. Okay, so it is April 11th, 2025 at 8:49 p.m. We had a little bit of a late start on our presentation and we had some questions and answers, but definitely a great presentation. I was really excited that he decided to volunteer to speak today. Excuse me. Alrighty, so let's go ahead and get started. Rich, would you like to read the meeting minutes from March 14th? And hopefully we can get those approved.
Yep. All right, 3AP General Business Meeting, March 14th, 2025. Business portion of the meeting began at 8:56 p.m. Meeting was online, hosted by Google Meet, live streamed to YouTube. 38 members in attendance. The presentation began at 7:30. Dr. Amruta Jayodend, who spoke about the Chandra X-ray Observatory. Business portion of the meeting was called to order. Minutes of the last meeting were read by Recording Secretary Rich Dawlish. Gail Reiger made the motion to accept the minutes from the February meeting, seconded by Alicia Bartolozzi. And I can't pronounce your name, Alicia, I'm sorry. Motion passed unanimously. John Holtz gave his look at that presentation about upcoming astronomical events. Highlights included Venus at Inferior Conjunction on March 23rd, conjunction of the Moon and Pleiades on March 21st, Jupiter, Spica, and the Moon will be very close tomorrow night, April 12th. John finished with a nice example explanation of the parallax of the Moon between our location and the equator, using eclipse images that had stars and were submitted by members and diagrams used in media. Kristen did not give a status update this meeting. Vice President John Wenskovich reported that the speakers for the rest of the season's meetings are booked and he has some leads and spots filled for the 2026 season. Rich Dawlish had nothing new from the recording secretary office, but announced a VA Star Party coming up in the following week. Date that did happen. I don't recall the exact date though. Dave Rager again thanked everyone who has helped respond to queries into Facebook and email. Terry Mealy was working on the first quarter treasurer's report and will have it done at the end of the month. Michael Scovern jumped in and spoke about the membership application and database issues. It seemed somewhat sporadic, with Gail reporting individuals could be added, but not family members. Michael also needed to touch base with Terry Mealy with regards to canceling the Wagman's phone from Verizon, porting it to the new system. Joyce Osborne Fisher asked John for information on upcoming speakers for GuideStar publication. Gail Reger reported that the online application was still down. Kristen presented the slide listing the names of the 2 new members to be voted on by the attendees. The number was low due to the database issues mentioned by Gail and Michael. I made the motion to accept the new members. John Holtz seconded and the motion passed unanimously. Observatory reports. Director Eric Fisher reported that they recently had the work party, the first in many years. Rug was pulled from the Bashir room in preparation for the repair work. Also, the scope was wrapped in plastic to protect it from dust and dirt. Contractor had been selected by the Wagman Committee. The crew also cleaned out the storage room, most of which will be offered to members at no charge or small club donation. The goal was to have everything cleaned and ready for the April 5th Star Party. Director Brian Crawford at Mingo picked up the remaining 2 planetary globes for the planetarium display. He showed one on camera and it was stunning. And they look great in person too, just as a side note. There will be a work party Saturday, March 22nd at Mingo for the planetarium remodel. Brian also asked again for member astrophotos for the postcard swag at NEAF and the observatories. Old business was NEAF preparations coming along. 3AP calendar is up to date with observatory and offsite events listed. New business, time to start club election process. Kristen nominated myself to chair the nominating committee. I accepted. Joyce Osborne Fisher questioned if a sitting officer is allowed to chair the nominating committee. There was a pause in the meeting as several members searched the bylaws. Our bylaws state that the president makes the nomination with no other restriction. With that confirmed, she again made the nomination. I accepted. And I asked Brian and Heather Davis to fill out the nominating committee. We will again use electionbuddy.com for the club elections. The cost of the club is $100. And all that's required really is importing the emails and filling in the nominations. Motion to adjourn at 9:58 p.m. by Gail Rigger and seconded by Terry Mealy. Motion passed unanimously. That's all.
All right. So the only thing was for Brian and Heather, we didn't do that during the meeting. That was afterwards, correct? Because
Oh, yes, for the nominating committee, that was after the meeting. Yes, that was
Okay.
after the fact.
okay, so I would say amend like that statement for those 2 things. I was gonna move on that like during this meeting, but other than that, I don't have any objections.
It's not part of the official notes. I just commented on that as I was going through.
Oh, gotcha. Okay. Okay. I just wanted to make sure. Okay. All right. May I get a motion to accept the meeting minutes from March 14th? Eric? All right. Second, Frank? All those in favor say aye, thumbs up.
Aye.
Aye.
I,
All right. Objections, say nay. Are there any abstains? Okay, motion passes. Thank you, Rich.
Thank you.
All right, John, I saw you were on. Did you have anything for look at that for this
Ye-
month?
Yes, I do.
Awesome. I can stop presenting if you would like to. Oh,
I think
oh,
I've
I think
taken
it's gonna
over
go.
already.
Yep, that works. Okay, go for it.
All right, so let's look at the things that are coming up this month here. If I can get that out of the way so I can click. There we go. Tomorrow night is the micro full moon for those of you that follow such things, meaning it's the moon, full moon closest to apogee, and the star Spica will be nearby. Also, as I mentioned last month, the moon is currently traveling highest or farthest north in declination and farthest south in declination. So when it's in the teapot of Sagittarius on April 18th and its farthest south declination, you may notice it being unusually low to the south. There are meteors shower coming up on the morning of April 25th. Venus and Saturn are back in the morning skies, and the moon joins them, forms a nice triangle. And 3 nights later, on April 28th, in the evening after sunset, the moon will be 4 degrees below the Pleiades. And let's see, April 28th, that's roughly a day after the new moon on the 27th, so it'll be a nice thin crescent. Some other things to look for. The other one in particular is probably May 4th and 5th, when Mars is going to be passing through the northern reaches, or maybe the northern suburbs of the Beehive cluster M44 in Cancer. Then Aquariid meteors, and the moon is going to be very close to Antares on the late night of May 13th. Now over to a few number photos that I got from Discord. Have a nice image of M82 on the left and M81 on the right. Dave Rager got a close-up of M81. I see that Mike Miller hypothesized that the pot of gold is located in Freeport, but since Mike is online with the meeting tonight, I assume he did not find said pot of gold in Freeport.
Perhaps.
Perhaps, yes. If there was a meeting in person and you drove up in a Cadillac or something like that, then maybe we would know differently. Full of nice solar images. Pat got one in hydrogen alpha light. Lots of detail across the disk. And John Macerda got a nice solar prominences, and other people did as well. But I forget what day this was, but pretty large prominence there. And that brings us up to any other observations. The only one that stands out in my mind that I actually did was on April 1st, went out and looked at the moon and the Pleiades, and the moon was probably only one diameter north of the Pleiades. It was very close. And, the sky was a little hazy in Point Breeze, so I couldn't see the Pleiades with the naked eye, but they were visible in binoculars. Anyone else have any observations they want to talk about? Anyone do any Messier marathons or anything else?
This is Ken Cole. So just to note that Venus is it's getting very elongated in the morning sky now. I think Wednesday morning I was at about 6:30 and it was already 15 degrees above the horizon.
Yes, it disappeared pretty fast in the evening skies, and it's coming back quickly in the morning skies. Part of that is just because it's relatively far north of the ecliptic at this particular apparition. That helps with the being visible in the morning. Thanks, Ken. Anyone else have any observations to mention?
Too many clouds.
Yes.
I saw the Monsoon Nebula.
Yes, I think we all saw that. I'm out in Philadelphia this week, but someone else in my company was saying they heard about snow flurries in Pittsburgh.
Instead of astronomy, I'm going to start a new hobby called cloud identification. So I'm
Yeah.
learning all about cumulus and cirrus and all that.
There are cloud observing societies in the world. Cloud appreciation societies.
I had a friend that asked if the either of the observatories had classes in cloud identification or weather forecasting.
That sounds like a great idea.
I said, just look at our star party charts.
Right.
You try to get into the weather, these forecasters are going to file a grievance on you.
Right.
All right. Thank you, John. Much appreciated as always. All righty. Let's go ahead and move on here. So officer reports. John Weskovich is, I think, currently, or he might be getting off of a flight right now. So he wasn't able to attend tonight's meeting. He said 2025, he has all the presenters scheduled. So he is looking for presenters for starting January 2026. For the May meeting, I believe the title for that presentation is a case study of interstellar material delivery on Alpha May meeting. Joyce, I don't know if you're on there with Eric, but if John hasn't sent you the information yet, I will send that to you so we can get that in the guide star.
Yeah, she
And
tells
I'll,
me that we did receive it. We're good.
okay, awesome. Alrighty, I'll make sure I add it to Discord then. Alrighty, Rich, did you have anything for recording or VA? I don't know if Rich, are you there?
Sorry, I am there. I'm babbling on, muted. Nothing for recording secretary. George Chase has been gone through the VA volunteer process. I believe he's out of town this week or next week, but we will be starting training him on the VA observatory. So soon there will be 2 of us. And then also Daniel Den. I don't believe he's on tonight. He wants to go through the process. So there will soon be 3 of us able to operate the observatory at the VA. So that'll be exciting.
Yeah, that's awesome. And at least that way you guys could take turns, that way you don't feel always obligated to, get out there.
Yeah.
Wonderful. Alrighty. Dave Rager, I think he was on earlier, but I don't see him on now. I could be wrong. I don't see him. So, all right. Gail, I think I saw something in the chat from Patrick. Patrick wrote, website is working fine. Please let me know if you are not getting any emails from the list server. I think that's from Gail, I'm assuming. All right. Yes. Okay, thank you, Gail. All right, Terry Mealy. I did not see Terry on. So I know last time I spoken with him, I believe was during the executive committee meeting, and I think he was still getting a report together for the first quarter. I haven't received anything just yet, but I'll follow up with Terry to see if he has the report yet. All right, Michael, I think I saw you sign on. Did you have anything to report?
I'll just update that we had about 3 outages recently of the website. I have identified what's been going on. I made some changes and some tunings, and I think we're not going to have the problem again, but I'll be keeping an eye on it and I will adjust as necessary. We should be good though. That's all I have.
All right. Thank you, Michael. Much appreciated. All right. Joyce, is she nearby, Eric?
No, she's not on, so I'm going to be her proxy on this. She says that we're going to reopen requests for articles for the Guide Star about backyard observatories. So we had about 4 or 5 such reports. One of them was Brian and Dave Marcijanek. But now that people are getting out of the house and opening up their backyard observatories, feel free to write an article. Again, Joyce says, don't be afraid if you can't write. We'll piece together something for you. So that's we're going to restart those stories. They're very interesting to tell.
All righty. Thank you, Eric. Okay. So we're going to go ahead and vote in our new members. So this was from last meeting from March 14th. So this is a month. So we gained a couple newbies. Right now we are at 369 members in total, not memberships, but members. So we went up a little bit. which is great. So maybe once the rain stops, maybe we'll get some more viewers. I believe there's, yeah, 7 altogether. Is everybody able to see their names on the screen? Okay. Can I get a motion to accept these new members into our wonderful organization? Frank, I see your hand. Ken, I seen your hand go up. So I think Frank and then Ken. All those in favor say aye, thumbs up.
Aye.
Aye,
Aye.
Hey,
aye, aye, aye.
Any objections, say nay. Any abstains? All right, motion passes. Welcome to our new members. I always have to ask, is anybody that's listed here on tonight? Let's see. I'll just take a quick peek. All right, it doesn't look like it so far. Okay, so hopefully we'll get to meet some of these newbies at some star parties coming up. Okay. All right, observatory reports. Wagman, Eric, do you want to give us the 411 as to what's been going on?
The 411, what's the 411?
I'm asking you what the 411 is.
Anyway, very quickly, I've got good news and I got bad news. The good news is that we're close to returning the Bashir room to service. Of course, we had the water mitigation work done in the crawl space. Then we had the floor repaired where there was water damage to the wood, and now we've just put the first coat of paint on the Bashir room walls. We took down the Saturn mural because it was starting to get deteriorated, and we're thinking about putting something new on that wall, but it's going to take a couple more coats of paint. But figure next couple of weeks, the Bashir room will be back in service. The bad news is that while we were working up there, and it was a rainy day, we noticed that our new sump pump was cranking like crazy, which suggests that we have a clog in our drain line on the north flank of the hill. And to repair that clog, we're looking at several options, but the worst case is that we would have to have a company with a backhoe and trench out and dig down to the pipe, replace it. It's underground to a sump. And we're talking probably 5 figures to do something that big. So I'm consulting with my engineers like Dave Marcijanek, Wade Barbin, Phil, and all the guys in the committee to see if there's any way we can get this drainage problem solved. But thankfully, because we have a sump pump, we've been able to keep the crawl space relatively dry. We had our first star party on April 5th. It was a rainy night, but had some members show up. And just as a reminder, we have what I call Brighton Box protocol, which is that we will only close the observatory if there's a tornado warning. So we open up the observatory like Mingo. We take the covers off the telescopes, run some displays, hand out some literature, so that we don't have the problems we had last year. Is it canceled? Is it on? Is it canceled? So we had, I think it was Patrick and Gail and John Wenskovich showed up, and we had a nice time chatting while we heard the rain falling on the building. Let's see, what else do I have? Next Wagman start party is April 25th. Hopefully the Bashir will be back in operation then. And also I'm putting out a call to the membership in general for help with getting a new batch of ball caps. I want to get name badges and lanyards like Mingo has. We're going to put pins, if you go to some fast food stores, you can tell somebody's an achiever because they have a bunch of pins on their ball cap. So rather than issuing new ball caps every year, we're going to get little AAAP pins to put on the cap. So anybody that wants to help the Wagman committee help me with procuring these things, let me know. And also the plaques that we have in the Bashir room need to be updated. Got to find a new engraver, a new trophy company to get that work done. If anybody wants to help with that, let me know. And Mike Miller or Phil, do you have anything else you want to say about anything else in the building?
Nothing right now.
Okay. So that's it. Bob
Oh.
Flyman.
Oh, you missed Bob.
Oh, Bob, I didn't
Hey,
know you're online. Sorry.
yeah, Eric, are we, when are you planning on having the carpet people come up? Are you gonna hold off until after we get the second coat on, I hope?
Yeah, we're going to get two and maybe three coats of paint. Also, the ground has to be, according to the carpet company, 3 days of at least 65 degrees ambient temperature, so
Oh.
that when they adhere the carpet to the concrete section of the floor, it'll stick. So,
Okay,
don't know when that's going to be.
okay.
Supposed to.
So we got some
support-
time, till the weather warms up, so we can get that second coat of paint on there.
By the way, all thanks to Bob Fryman, he helped with scraping down the walls of the Brashear room. We had to get the loose paint off, and that was quite a sight. Bob and Tom Lavelle and Dave
Tom Lavelle,
Marcinjanic, and
Yeah.
the paint just came right off the walls. You could almost pick it off with your fingernails. So we're doing a better job this time of making it stick.
Yeah,
And if it
but we
works,
gotta wait, yeah.
we can tell if Mingo has the same problem. We found a new way to stop that dang leaching in the joints.
All right. I think Joe had his hand up. Joe McQueen.
He's
Yes,
muted.
I just had a question. Do you send out emails about when you're going to have like work parties or
Yes, right now it's just going to the. That's a good point, because right now I just send it to the Wagman committee for the work parties. But if members at large want to help out, I could make that even larger to include all the members. I don't know how Mingo does it, but right now I'm just limiting them to the Wagman committee. But maybe you have a good idea there.
yeah, I mean, I wouldn't mind coming up, if I'm free, helping with painting or, scraping or something. So
Mhm.
I'm sure there's other people that would also help.
Yeah.
Yeah, I was going to say, if anybody here is interested in helping at any of the observatories, work parties or cleanup, just reach out to the directors. If you need their email, it's usually like Mingo director at 3ap.org. Yeah. And then, Wagman director, which Eric, do you have the Wagman director email
No,
account now?
Heather canceled that for reasons that she was talking computerese to me, and I didn't understand why. But the Wagman director is defunct. We're just Eric Fisher at 3ap.org.
Okay.
So
Yeah, so if anybody's interested, spread the word. If you talk to any members, if they are interested in helping out, which I'm sure they will take, any help, just reach out to the directors, and they can let you know when the next meetup is going to be. Same with the associate directors too. Yes, I'm calling you out, Mike and Heather. All right.
yeah, I have such a good team working for me at Wagman. There's so much knowledge there. I feel like a dunderhead listening to these talk and telling me what's the right way to do things. So it's good to have a bunch of experts on the team.
Yeah, and Heather just commented in the chat. Another good way to communicate is, of course, the list server or Discord. And most, I think, all except for maybe one, I'm not sure. All the directors mostly are on Discord, so that's a really easy way to get a hold of somebody, and leave them a message.
Right. By the way, I was on Discord the other day, and I see that we crossed 200 members, subscribers.
Mm-hmm. Yeah. Alrighty. Okay. We're gonna go ahead and move on to Mingo. Brian, do you have anything you want to talk about?
Hey, Brian, are you putting a new surface on the dome itself, the image surface, or is that still the same? Oh yeah. Well, we've done a lot of clean out, so we'll probably stack them in the storage room. So yeah, let's talk.
Alrighty. Thank you very much. All right. Heather put in the chat that she doesn't have any updates, so we're going to go ahead and move on here. All right. Old and new business. So obviously, how was NEAF? To those that participated, I've heard some stories, of course. It sounded like it was very productive in terms of talking to some sponsors and also kind of just getting our name more out there. But would you guys like to elaborate for a couple minutes?
Ionis. Bionis also approached us other than Dwarf Labs. They came to us, so that was good. Yeah, Rocco's Legos were definitely the draw. That sucked people in. So we're gonna get enough bricks to do a life-size model of the Brashear for next year to have up in the back of the booth. So we'll need Wagman people to get on that for us. Other than that, yeah, it was my first time at NEAF. I I really enjoyed it. It was an interesting experience. I'm glad I went.
Wonderful. Phil, I'm volunteering you for the brochure model there.
Start taking measurements. First things first.
Jody chatted with, so there was the Antique Telescope Society. They had a small brochure refractor there. And so Jody spoke with the owner of that and got some information about what the miscellaneous piece, which we think is a astrograph for our brochure telescope. He'll have to report on that. I didn't get the chance to talk. But we know what it is now.
All righty. Sounds good. Looking forward to hearing some more stories. Definitely, I had listened to a lot of stories on my way home from Monroeville, but it sounded like you guys had a successful trip, which is great. And I'm glad everybody made it back safe and you guys got there okay. So thank you very much for, representing the 3AP to all of you who went and, watched the booth and, getting some club feedback. It's great. It's great. All right. So we're going to go ahead and move on. So last meeting, like we mentioned, we went ahead and started talking about the election of officers for 2025-2026. I had nominated Rich Dolish for chairperson for the nominating committee. At that time, I did ask the floor if anybody was interested in being part of the nominating committee, and it was dead silence. So with that, as the general membership, we were unable to vote in, I guess, accepting committee members under Rich for chairperson. So Rich went ahead and reached out to Brian Crawford, also Heather Davis. And Heather, I think she's not new, but I had met her last year. So she has been a member for at least over a year, I believe. But I just wanted to have it on record that the general membership is accepting them as committee members. So if I can get a motion to, and I'm not sure if we have to do them one at a time, but I'm just going to kind of cheat it and do both just to save some time here. But I would like to ask for a motion to accept Brian Crawford and Heather Davis as committee members of the nominating committee. Eric, I see your hand up. And Tom, I see your hand, so I'll take that as a second. All those in favor say yay, aye, thumbs up.
Aye.
Aye.
Hey,
All right, are there any objections? Any abstains? Okay, motion passes. Thank you guys very much. I know we should have done it last time, but unfortunately they were not present. Heather's not present tonight. However, and I probably should have said this too, both of them did accept being committee members. So again, we're kind of going this in a curve, but I just wanted to have it on record that we did accept it. All right, so going into new business, which is the main part of the May meeting. I'm sorry, well, yeah, April-May meeting is the nomination of officers. So I'm going to turn this over to the nominating committee, which I know Rich is on, of course, and also Brian. So, Rich, do you want to?
Yes.
Okay.
The nominating committee met. We discussed the process, what we'd have to go through, we discussed some possible candidates for the different officer positions. It really is my goal to get other people running for these positions, to actually have elections. So we reached out to a number of members to see who would be interested, if any. We did have one person accept. So for the nominations for this year's officer elections, President Kristen Crawford, Vice President John Wenskovich, Recording Secretary myself, Membership Secretary Gail Rager, Corresponding Secretary Dave Rager, and Member Alicia Bartolozzi. We know her as Lish. She agreed to run for Corresponding Secretary this year. So at least we have a race in one ballot. The ballots themselves will go out by next Friday, May 18th. If you have an email on site or on file with us, you will get an email from electionbuddy.com, possibly mentioning nominating chairperson at 3ap.org. If the email is bounced back or you do not have an email on file, a paper ballot will be mailed out to you. This is the process we used last year. It was very easy. It was, I feel it was a very successful election last year, very smooth. So we'll be doing that again. Does anyone have any questions about the process or the ballot?
Nope.
All right.
And I believe at this time, we, like for this meeting, we would be accepting nominations
yeah,
on the floor. Or
Thank you. Yes.
so if anybody who, you know, Rich, like you said, he did reach out to several individuals as part, you know, as part of the nominating committee, Brian and also Heather. But if anybody here, this is the time, if anybody wants to put a nomination up for, you know, for an officer.
Nope.
And the nomination, that person would have to be present to accept the nomination as well too. Okay. Going once, twice. All right. We'll go ahead and close it this way. On the ballots, and I believe Election Buddy, it allows you to still fill in
Yes.
as well. So
We
that,
can have write-in candidates.
yes, so that is still an option, just so everybody knows. All right. Oh, go ahead. I'm sorry.
I was just gonna say, and we will also have in-person voting at the May meeting. Eric, you have a question?
Yes, for the May Guide Star, we typically put in brief bios of each of the candidates, what their aspirations are. So what Joyce will do, is, I'm careful to phrase this, is send out what we put in last year's Guide Star for those that are running again. And Joyce will contact Alicia for something to say about herself. So
I already have Alicia's. I asked her for that. So I will forward that on to Joyce.
thank you.
And the bios will also go into the ballots.
Oh, that helps. Yes, thank you.
All right. Sounds good. Are there any other questions before we move on for the nominations, the elections, etc.? Okay, perfect. All right, so the only thing left that I have for new business, and then I have a feeling once Star Party season really starts to kick in gear, there's going to be more topics coming up. But for the May meeting, so I wanted to kind of just put the idea out here of where we would like to hold the May meeting. I did reach out to Luke Hoban The Allegheny Observatory will not be available in May because that's when they start doing their tours. Like that's their tour season. So they won't allow us to have a meeting there. However, he did say that he would be able to give us Alumni Hall if we want to meet on Pitt's campus. We met there last year for last year's May meeting. Another idea that has been brought to me is to potentially hold the meeting at one of the observatories. I do believe that in my opinion, I believe Mingo would be very ideal since we have the planetarium there. There's parking, and there's also, of course, handicap parking. It was just more of for the individuals that are on this meeting right now. Most of you, I know, usually do attend the in-person meetings, so I kind of wanted to gauge your thoughts or if there would be any objections to if we wanted to hold it in Pittsburgh like we have done in the past, or if meeting somewhere, like I said, at the observatory would be a better idea. I'm not against meeting at Wagman. The only thing that I would be potentially afraid of is if it rains, and if there is, let's say, 20 or 30 people that do come to the meeting, we may not have enough room inside the observatory to hold the meeting. So
Yeah,
that's why
we can only do it out. It would have to be an outdoors meeting on that patio. There's just not enough room in the reception room to do it. And right now, Wagman is sort of in disarray because we're remodeling and throwing out stuff. So this year it's out of the question. So if it's going to happen at Wagman, we'd have to hope for a clear night, a warm night, and do it out on the patio area. So Mingo is the better choice.
And since Mingo as well as Wagman has internet, if for those of you if you wanted to attend it in person for voting, of course you would have to be there. However, if you wanted to listen in on the meeting, if I will still have it available online, so I'll still do online plus in person. I would do the same thing if we were to meet in Pittsburgh as well too. I just know with all the construction going on right now, at least at least for me coming up from like South Hills area, it's been crazy. I don't know how much of it up north it's been. Also, just parking was also another I shouldn't say a problem, but just I know sometimes it can be hard to find parking unless you park in the garage. That's I think 2 blocks away from the hall. So it was just more of I was trying to see if there was a better option, or maybe if everybody here would prefer to stay in Pittsburgh, that's fine too. But I'm just kind of gauging everybody's vote at this point as to where we would like to meet before I post something and say we're just going to go here. So I was more or less making this what's your thoughts? I can do a vote on it to see what everybody wants to do, but trying to find an area. I know somebody had suggested maybe to reach out to some of the libraries. I could try doing that, but again, it's going to be a north versus south regardless if I can find a library available. So that's why I was kind of gauging, well, we know where the observatories are and we know where Alumni Hall is for the majority of us. So I was kind of narrowing it down to places we know of.
Yeah, if you do a hybrid meeting, Kristen, I think people would be amenable. Some people going to Mingo.
Yeah,
Okay.
I agree. I think Mingo's an ideal spot since either observatory, I think. I mean, granted, Wagman might be better in September when we can throw up some canopies on that patio, but yeah, I think Mingo's a great idea.
What were you saying, Frank?
I'd go along with Mingo.
Okay. Does anybody else have any thoughts? Ken?
I don't think you'll get a library that will want to stay open till 10 o'clock at night.
Yeah, and that was my other thought too. Yeah, totally agree. Is the May speaker presenting online? So John had I forget who it is. I just got the abstract and the title. I'm sure I could look it up, but I can still send it as hybrid. I don't think he mentioned that the speaker was going to be like flying in or anything like that. But I can reach out. But either way, like I have it available for online, whether we were in Pittsburgh or if we were somewhere else.
Just one comment. Probably not going to work for next month, but Cohatch, which is at the waterfront, is like a co-working space. They do have scholarships for nonprofits and allow, I think, up to two like times a year you can have a meeting there. It's a very large space. So it's an option for future meetings just to kind of keep in mind.
Okay. You said it's at the waterfront?
Yeah, it's in like the little shops area at the waterfront. If you guys are familiar with co-working space, it's for like people that work remotely if they wanted to kind of come and work around other people. So they have like nooks and crannies, and then they have like a theater, but the theater only holds, maybe 20 people. But then they have big open areas that we can set up with projector. There's internet there. There's projector stuff. So it's an option to think about for the future. I think they allow 2 per year. But I can get more details from another nonprofit that we've used it for.
Okay. That sounds good. Thank you. All right. Well, I'm thinking we're gonna go with Mingo then for May. So this will be on just so I have the date here. This will be on May 9th. Yes, May 9th. Friday. And then I'm guessing the presentation will start at 7:30. So I'll talk to the Mingo directors to see if someone will be available to open up the building. I don't see why there wouldn't be, but that's just me talking. But we'll at least have the doors open. I don't know if we have to let the park know, but yeah. So we'll just plan on meeting there. That way, rain or shine, we'll have somewhere to be. We'll meet in the planetarium. I'll bring my computer and stuff. And if something else comes up, I'll let everybody know. But that will be the meeting place. We'll do Mingo.
And Kristen, I'll have Joyce put in the guide star that if you're coming from the North Hills, think about carpooling.
Yeah.
And as an inducement to come, maybe you say after the meeting, if we can run one of our planetarium programs.
Yeah. Yeah. We can definitely talk to or get the opinions of the directors and, anybody who comes, and then also, let them know in case any of them don't want to make the drive down. I'll have it available for hybrid. So and we'll probably do it also like live streamed as well too. So there'll be plenty of options for members to be able to attend the meeting if they can't make it in person. All right. Okie dokie then. I'm glad we got that covered. Oh, Ken, do you have something? I'm sorry. I turned my head for 2 seconds.
Well, and, actually, I wanted to bring up a new topic, but maybe you weren't ready for that.
Let me see here. Yeah, I think I was just going to go event reminders, which remind me, I forgot to put your event down. Was that what you were going to talk about?
Yeah, yeah.
Was tomorrow? Yeah, go for it.
I just want to remind everyone you're invited up to IUP tomorrow to see the planetarium. If at this point you haven't gotten around to emailing me, that's fine. You show up anyway. I just wanted to make sure I wasn't going to exceed the capacity of the room and have to plan for that. Joyce helpfully put the information I gave her in the guide star that's available, or you can always shoot me an email if you can't find that about parking and so on. I know that Mingo has a work day tomorrow, and that's very important. And I want to plant again in the ears of those people. One of the things you could talk about tomorrow is if there's a time some of you could come up to IUP. I will happily do a rerun for the Mingo committee. This is a fancy overbuilt planetarium. It's more than we needed, but I can show you some things in there that might give you ideas for your planetarium. Why not think big? And if a weekend, they all seem to fill up, isn't going to work for Mingo committee or anyone who's interested, we could do a weeknight or something like that too. So I just wanted to encourage you to think about that and to think about coming tomorrow. Thank you.
Hey, Ken, if I ask you a question, how many people are coming tomorrow?
I've heard from about, I've heard from about 15 or 20 people, I think.
Okay, I didn't respond because I didn't think I had to, but I'll be coming too.
Good.
Okay.
Wonderful. Thank you so much, Ken, for doing this too. I tell you, like, March went by really fast, and then we had so many things going on the weekends, and then it was like star parties just snuck up on us. Even though it was such a long winter, it felt like it was just like, boom, here we go. So I definitely would like to try to make it up there eventually. So if you come up with another date, yeah, please let us know, because I would love to see it.
I really think it might work faster if you guys, I'm guessing if I suggest dates to the folks who couldn't come, it's a shot in the dark like this was. If one day of the week is better or something like that, it would be a big help. It would it would speed things up. But anyway, enough said.
And Ken, we'll gain a new appreciation for how far you have to come to attend Wagman star parties and meetings and so forth.
All right. Sounds good. Okay, I just I went ahead and put together just a couple event reminders. So I did this last year. I was going to try to continue doing this. So we got Wagman star parties coming up. So April 25th, May 2nd, and May 3rd. Mingo's first star party is going to be April 26th, followed by May 23rd and 24th. Offsite Avonworth star party is going to be Saturday, April 26th. And then offsite Peters Township is on May 30th. I don't know why. I was thinking there was one with a star party, but I could be wrong. Oh, yeah. It's Mingo's. That's where I see it. Okay. The Avonworth one is on the same day as the Mingo Star Party one. Okay. All right. So those are just a couple event reminders. I know Rich and Mike Christensen, you guys were still trying to coordinate some offsite dates.
Yeah, we're still looking. Mike wants to do a couple more state parks, so we're still trying to do that. I need to follow up with the Heart Camp people to see. They said they were interested in having us back, but I just want to shoot a friendly reminder. And Eric, for the 25th, Tom Shields from Allegheny County Parks, he's supposed to come out to the Wagman party to just get the lay of the land for a future setup with the Allegheny County Park people at one of our events.
That's a new name to me. I'm glad you told me that. I've not heard of him.
Yeah, we were communicating back in February. I can send you the information.
Thank you.
Okay. I was gonna say, I think Bob had his hand up first, then Mary, I think you were after that. So Bob, did you have something?
Yeah, just in regards to the Avonworth star party coming up on the 26th, we'll be setting up in the large soccer field in the complex there. So it's a nice wide open space for us. And it's going to be the Cub Scout group. There could be possibly up to 50 Cub Scouts, more like 35, 40, and a chaperone for each kid. So there'll be a parent, mother or father, I guess. So it'll be quite a large star party. I'm kind of looking forward to it. I've got about 4 or 5 confirmed members that are going to help out on that. So we're looking pretty good for that one. I'm kind of looking forward to it. So.
And just keep in mind now that if the weather's looking really bad, to notify Joyce so we can put out a cancellation notice if that's
right.
the plan.
Right. I know the kids are going to be, the scouts are going to be setting up around 5 o'clock. They'll be up on the hill, setting up their tents and doing all the other stuff that they do and setting up their little campfire. But we'll be way down on the soccer field, away from any of that stuff. So we should really have a good time. I plan on getting there around 7 o'clock. Sunset isn't until a little after 8. So it should work out really well. I'm just hoping, like you said, we get some clear skies. So.
Okay.
Thank you, Kristen.
Oh, no problem. All right, Mary.
Okay, is the Hillman Airplane Field Star Party still on May 17th? That's what I have it listed as on my calendar.
So you're not looking at last year?
No.
No, she's right.
I have it for May
Yeah.
17th. I just didn't see it on this list.
Yeah, I missed it too. I apologize. Yeah, May 17th, offsite Hillman. Yep, you are correct. So thank you for pointing that out.
Okay.
Yeah, you are correct.
I know the boys always like going there. Little grandsons.
And just to let everybody know, the first week of May is also the 100th anniversary of the first Zeiss Planetarium. There's a big event going on at La Roche College in the North Hills, and we might have some triple AP representation there. So that'll be published soon.
Okay. All right. Thank you, Mary. Thank you for having my back there.
I just wanted to make sure that, it was still on. So, okay.
Oh, I totally had that. That was from the last slide, but basically the last slide was time for adjournment. I had the guest speaker that was from last month. Of course, I just redo on the templates. I'm gonna see just really quick who John said the guest speaker was, and I'm drawing a blank on what is. Here we go. Let me see. Just want to see if they're okay. It's Cole Gregg. Is an astronomer specializing in small body dynamics, interstellar objects, and planetary defense. He is currently completing a PhD at Western University under the supervision of Dr. Paul Weigert, focusing on simulations of interstellar material traveling through the Milky Way. So that's who our guest speaker is for May, is Cole Gregg. Okay. All righty. Does anybody else have anything that needs to be brought up? No? All right, I'm just double checking. I didn't have anything else. Nope, I think we're good. All right, may I have can I get a motion to adjourn the meeting? Matt, thank you. Do I have a second? Frank, I think I saw your hand go up.
Yeah.
All right. All those in favor say aye. Yes.
Aye.
Thumbs up. All right. Any objections?
Good meeting, Kristen. This was a good meeting for you. Thank you.
No problem. I'm sorry. Any objections? Any abstains? All right. Motion passes. Thank you very much, everybody. And thank you, Eric. Much appreciated. I'm sorry it ran a little late, but I'm glad we got through all the things. And I'm looking forward to seeing you guys at Mingo if you guys can make it for May. And hopefully I mean, I don't know if we can get lucky. Maybe it might be a nice night and we can actually just maybe do some observing while we're there, because why not?